As promised, we are back from the break. Anyway, this is a supplement. It's a little more detailed look at an ASIC design flow, and it's just a representative of a high-level overview of an ASIC design flow. Every company would typically have their own. This particular ASIC is a combination of digital and analog circuits on an IC to achieve the desired function. The ASIC components might be CPU cores, peripherals, memories, and analog circuits to provide clocks and interfaces to the real world, and of course IOs. ASICs are very complex devices, and through its evolution to keep up with speed, various tools and methods are introduced in ASIC design to automate the flow, produce quicker and better results. Better meaning, more reliable, perhaps more testable, things of that nature. IC design moved from placing transistors by hand, so that's integrated circuit design, through to logic using standard gates with schematic entry, so that's something you may be familiar with, and much more recently to describing logic at high levels of abstraction, typically using a hardware description language. In this particular example, we'll look at a design that has an architecture which includes both the software and hardware component, so that interface has to be defined. So you have to model the hardware-software system at a high level, run simulations to see if performance requirements can be met. You define the software interface for the hardware-software interaction to achieve the targeting goals. With respect to the ASIC contents itself, i.e. the hardware part, you define the contents and see if it can be done with a single ASIC, and taking into account the cost of manufacturing. Depending on the technology used, it may be cost prohibitive to put it all on one chip. Maybe you have to use two chips, or you may decide to use an FPGA or a couple of FPGAs. Define all the interfaces needed to communicate with external components, because the ASIC has to sit somewhere. Burrowing down a little bit further to the microarchitecture, some of the specific details, you have to partition your design. Of course, that's very, very standard technique for design. It's basically making the things more modular and smaller and easier to deal with. You'll need some type of a reset strategy upon power up or reset. You have to put it in the machine into a known state. Some type of clocking strategy, verification strategy, testing strategy, and those things all have to come together to build your ASIC. So the design entry at the front end is where basically the microarchitecture is implemented in hardware. And to do that, use a hardware description language like VHDL, Verilog, System C. There's a number of them. Verilog's highlighted in red because that's the one that you'll be using in the course. The increased complexity in current designs require the use of HDLs to gain productivity. A real big advantage of an HDL is that it's independent of process technology and hence fosters reuse and can be reused over time. Some of the tools that might be involved, maybe text editors, some simple text editors, but more likely a fairly sophisticated IDE. There's also visual design tools like Visual HDL, for example, where you take a state machine represented in something that's a familiar form that you're used to maybe building an early prototype in, and then it'll generate the HDL for you. At this point in time, there might be some need for some semantic checks, just making sure language is correct. This phase can also be used to check the synthesizability of the code. So it's one thing to have code, and it's another thing to have code that you can actually synthesize into hardware. Some of the tools that you'll use for this will be Model Sim and NC Sim or VCS. Those are industry standard kind of tools. And over here it gives a good idea of what the big players in the industry are: Synopsys, Mentor Graphics, and Cadence. Verification is a process where the design is tested against specification. The verification methods are classified broadly as static methods and dynamic methods. A static method is one where you're trying to see if the Boolean equations match the design of the specification. Dynamic verification is much more likely to be encountered by you, and you use it all the time. You have stimuli generators, and they basically apply inputs and simulate the design in a simulator, and you obtain the results. So dynamic verification has a couple of different methods. One might be directed test cases. So these are ones that you think up. They're predefined set of stimuli, and the outputs are then checked against the specification. Typically you're going to look at corner cases, average cases, but it's very unlikely you're going to generate a very large number of directed test cases. What you do then is you add a large number of constrained random verification test vectors, and what that means is basically you have a tool which will generate the stimuli for you, as whatever constraints are associated with it, perhaps inputs from a distribution. It allows properties to be specified, circuit simulate it, and then you monitor the expected behavior of the design. Some of the tools used are listed down there again, and you can see that some of them are the same players that we had from the previous page. Some of the back-end steps sort of put synthesis, scan, insertion. It's sort of somewhere between front end and back end. Clearly the synthesis part is taking your HDL to a netlist, and basically that is a part of the synthesis step. The reason it's listed here as back end because it has some automatic scan insertion. What scan insertion allows you to do is implement some test fixtures that you don't explicitly design for but get added for you. The floor plan stage is sort of where the big pieces of the chip are located, and the placement is typically where the little pieces are placed and routed, and where you'd implement smaller size pieces of the design. A big part of any kind of ASIC is clock tree synthesis, and that's also a very difficult part. That's where you're trying to eliminate clock edges arriving at different times. We'll also look a little bit at static timing analysis. Excuse me. Effectively looking for the longest path in a graph, because what that's going to do, it's going to tell you how fast you're going to be able to clock that particular design. We'll look at design rule checking. That's low-level design rule checking, and these might be violations in the spacing when you're basically drawing polygon blocks that are going to be implemented in silicon. So it might be making sure that two metal layers are far enough apart that there's not a chance of them either touching one another, causing a violation, or perhaps even an electrical rule check where there might be some crosstalk that you're trying to avoid. And at some point you'd like to be able to verify the layout versus the schematic to make sure that they basically are representing the same structure. Now, with respect to a floor plan, it's really the partitioning of digital and analog cells in their placement. There's a power ring for core logic, I/O pad placement, power ring for I/O pads, and micro power rings that may be on the chip as well. One of the reasons for that might be that you're able to use a chip that has basically different VDD on different parts of the chip, or you might be able to power down sections or put them to sleep. With respect to synthesis, if the HDL is going to be mapped to a standard cell, the mapping is done as per constraints given by the designer. So this is a scenario where the ASIC is going into a standard cell library. And in this case, the library technology node would be known, 45 nanometer, 32 nanometer, maximum capacitance and maximum transitions. And what you can do with those libraries is put them into your simulators and see how well your design will do without actually having the physical idea how the little logic block is placed and routed. That you may not have access to that, but you will be able to generate some performance constraints or specify them, such as clock frequency and I/O timings. Maybe specify what operating conditions the device is going to operate under. Perhaps it's going to be an extreme temperature range, so those things have to be accounted for. Typically, you also want to place something such that the area is minimized, so there may be some area constraints and whatever other placement information you got from the floor plan. The scan insertion, this is an automated part of the design process, and this is because you typically have some synchronous circuits and you'd like to test them with a scan-based method. What that allows you to do is scan in a test vector, test the combination logic part of the sequential design, and then capture that again in some flip-flops and then scan them out and observe them. So the objective is to test for manufacturing defects rather than functional ones. So this type of test facility or utility is used once the chip is manufactured. So some of the fault models that you'd use during the testing and modeling to see if you're getting sufficient coverage might be a stuck-at fault, where you just simply model a wire as being stuck to VDD or stuck to ground and what impact that might have. More difficult ones would be an at-speed test where you're worried about parametric faults. So a transistor may be slower than you had anticipated it's designed to be for a number of manufacturing defect reasons or just natural variations in the device when it's manufactured. Placement of hard macros, that's something that's basically pre-assembled. You really don't design, but you want to use maybe memories and I/O pads. They're placed during the floor plan phase. The reason they're hard macro is they're highly tuned, usually pieces of silicon, and you don't want to reinvent the wheel. The logic is placed in the logic area, defined in the floor plan phase by using automated placement tools. So this is the hardware that you basically are specifying as a netlist that you want to get implemented in silicon. If it's a placement of standard cells, it can be driven by a number of different constraints, such as perhaps minimizing area, minimizing wire length, and more recently timing-based type of specification. So you may have to take into account that even though you get a really nice compact design, there may be one net in it that is causing you a performance problem, so you may have to redesign it, or it might be too power hungry, so you have to change the way it's implemented. Clock tree synthesis is a very important part of ASIC design. It's very difficult because what you like to do in a synchronous design is have all the clocks arrive at flip-flops at almost the same time, but the flip-flops are spread out all over the chip after placement, and the clock arrival times can be quite different. So to make the clocks arrive at around the same time, clock tree is needed to be built, and this phase is called clock tree synthesis, and we'll look a little bit more into that later and some examples of it. Certainly some very nice types of clock trees are synthesized, and it certainly gives you a lot to think about when you're building an ASIC. In this phase, the tools build the clock tree by adding buffers to the clock path and delaying the fast arriving clock to match a slow arriving clock. Some of the complications arise because the chip is very big and the clock rates are very high. The routes are messy, and some of the effects of this are that perhaps a large number of clock buffers is going to be added, so that adds more devices onto your chip. It could cause additional congestion and may introduce some timing violations on their own. What you want to try to do is minimize rising edge clock skew in this particular case, and that's basically a clock arrival difference. And of course, since these are placed all over the chip, the wire lengths are all different. There might be some temperature variations, even locally. And so it's an awful lot of state-of-the-art engineering goes into building the clock tree. Routing is another part of the ASIC design. This is when once the instances are placed, you need to be able to connect them up through wires. And again, automatic tools take the connectivity information from in this case, a Verilog netlist, and connect the pins of the instances. So those instances are modules or gates or standard cells, and routing is basically responsible for connecting those up. So tools normally do a global route where it estimates congestion and connects the pins, and then a detailed route usually takes place to place metal wires that connect up the pins using routing channels, or at least that's one means of doing it. With so many routing layers nowadays, I think they do tend to route over the cells much more than they used to in the past. Static timing analysis, we'll spend some time looking at basically generation of delay numbers, and that's like RC extraction. And the terminology that you might hear is back annotation. Back annotation means once you've got a layout, you back annotate, you bring in the parasitics onto your net list, and then you can simulate your circuit with the parasitics included. And typically they're going to be capacitances. So it's ideally done from post-layout netlist, and it allows you to see if you're meeting your timing constraints. It gives you some ideas on setup and hold violations. The setup is where the data path is too slow. The hold is where the data path is too fast. And then there's a number of circuit design techniques that you can use to mitigate those problems. Another part that you have to worry about is equivalence check, making sure that your RTL, that's your hardware description language effectively, and gate level net lists are equivalent. So it's the intermediate representation, and you want to make sure that they're the same. An equivalence check is a method which compares the Boolean equation from RTL and the gate net list. It utilizes a number of invariants, like primary functional ports are the same in RTL and the gate level, registers and flip-flops are the same in RTL and the gate level. I don't have a lot of experience in equivalence checking, but certainly can appreciate an important part of the design process. Physical verification. Tools convert the layout into a set of transistors and checks with the supplied reference schematic. You want to make sure that your layout, where you have polysilicon crossing diffusion, or transistors and the transistors that you wanted, and they're connected up appropriately so the net list of the layout matches the net list of the schematic. Design rule checking is sort of the low-level physical check where you're making sure that the design rules of the technology, i.e. let's say you're using a 32 nanometer node technology from TSMC, you know what the design rules are, and it might say that the minimum metal spacing has to be so much, and if you run a design rule check and there's a violation there, you'd have to either redesign that part or have the wires move the part of that part at that instance where it's located as being a design rule violation. There's also electrical rule checks that could take place where you're making sure that perhaps you're not pushing too much current through particular net lists, or making sure that you have large enough power and ground rails to supply the power to the chip. Remember, these ASICs typically are extremely power hungry. So how does all of that relate to us? Well, certainly technology is important, and just being able to speak the language helps a little bit. In a fair bit of detail, we'll look into various aspects of physical devices and some of the inner workings of low-level CAD, and we'll spend a fair bit of time fleshing out some of the details, some examples of the clock tree synthesis, maybe some the tool flow for doing that, static timing analysis, and some of the circuit techniques that you can use to ensure that your circuit is going to operate faster than it would have otherwise. It's always a design trade-off. Anyway, that brings us to doesn't bring us anywhere yet. Anyway, through the lab, you're going to be very familiar with Verilog and hopefully ModelSim. This little bit that we looked at provides a big picture of context, and for us the most common ASIC is going to be an FPGA, but much of the design flow is the same. There'll be things that aren't there. The scan insertion, for example, won't exist, but you certainly will be aware of them. And that brings us to a break. Okay, thank you.